Thank you for coming to our seminar presentation on the piezoelectric applications of zinc oxide nanowires on fabric. I'm Nan, this is Josh, and my two other group members, Emily and Tevis, are outside manning the booth. So, with the integration of technology into our daily lives, consumers have been demanding more immediate access to their electronic devices. And what happens when their personal electronic devices run out of power? Well, they're either left with two options. One, they wait until they get to an outlet to charge the device, so they're stationary, or two, they use a bulky battery pack. With the wearable electronics industry experiencing significant growth and investment, we believe that there is a market for a reliable and convenient power source that can replace bulky battery packs while being a more attractive option than charging at an outlet, just because you're stationary when you're at an outlet. So our project objective was to design a wearable textile that could harness the power from the movement of the human body and translate that into usable power. So essentially this textile would have to provide power and not require charging. So we wanted to make it as an add-on component to already existing clothing, and we wanted to focus on a low cost of integration and production of the device. So from that, we were able to define some customer requirements. So our primary customer requirement was that we wanted to generate a minimum of 3 microwatts of power. And we picked this number just because our research indicated that this was enough to power glucose sensors and other small-scale electronics, or maybe just provide enough standby power so that we could actually test something when we finished our product. And then our secondary goal was to generate 50 microwatts of power. That would just give us more options on what we could actually test. And we also wanted our prototype to be durable, which is where the fabric lifetime of 1 year with 50 wash cycles comes from. And the other ones are just we want it to be lightweight, we want it to be cheap, and then the tertiary goal is to have environmentally friendly disposal.
So in order to meet these goals, we decided to utilize the piezoelectric effect for our solution. So the piezoelectric effect allows you to generate an electrical power without the need of a bulky battery pack or a replacement. We chose to use zinc oxide because it exhibits the piezoelectric effect, and we chose to use cotton as our fabric due to its morphology. So let's take a look at how the piezoelectric effect works. So the piezoelectric effect is the ability to take an applied mechanical strain and convert that into an electrical signal. So in this way, the movement of the human body and clothing on top of it could be utilized to power small-scale sensors. So if you look at this schematic, the piezoelectric effect works by taking a mechanical stress applied to a piezoelectric material with a polar axis, and then through charge accumulation, it generates a dipole moment that allows for you to generate an electric field. This electric field then builds an electric potential, enabling current to flow. So there's various piezoelectric materials. Some of them are ceramics, polymers, and crystals. And we chose to use the ceramic, zinc oxide, and the nanowire form for our solution. So let's take a look at why we chose to use zinc oxide nanowires. So first and foremost, zinc oxide nanowires exhibit this piezoelectric property that we need. Secondly, the nanowires are more flexible, which would be ideal for our application. And zinc oxide has been shown to be safe for human use based on literature. So this can be compared to other piezoelectric materials that are used in textiles, such as PVDF. So PVDF is a skin irritant, which can be compared to zinc oxide nanowires, which is not shown to have an effect when it's exposed to the skin. So let's take a look. Oh, and also we chose to use larger nanowires. So initially we tried to use smaller ones, but then based on our testing, we switched to large. So we used nanowires that had 4 to 5 micrometer length and had 300 nanometer diameter. This was because they have increased conductivity as well as an increased piezoelectric response due to the greater built-in potential. So let's take a look at why we chose to use cotton. So the main reason of cotton is due to its morphology. So cotton is composed of multiple fibrils, and in the image on the right you can see one such fibril as the large structure, and of that it's composed of multiple microfibrils, which is the small thread shown throughout. This gives it a high surface area, allowing for many van der Waals interactions, and as a result you get strong adhesion for your deposited material. And this can be compared to other materials that are used for textiles, for example, nylon. Nylon has a much lower surface area, and as a result has worse adhesion.
So our fabrication process had to be simple and straightforward because, as you can imagine, the manufacturing step plays a huge role when you're trying to minimize the final cost of the product. So therefore, we chose and focused on a simple dip and dry deposition method of our nanowires onto our substrate. So our fabrication technique essentially had 3 steps. 1, you have to prepare the ZNO nanowire solution. 2, you submerge the fabric in the nanowire solution to coat it. 3, you allow it to dry and apply colloidal silver paste as contacts. And we realized that the success of our fabrication would also be dependent on our ability to achieve even dispersion and suspension. So we worked on refining our suspension technique. So just from doing this multiple times, it took us about 10 minutes to do this coating step. So therefore, it was mandatory to obtain a suspension that could will essentially remain suspended for the entire duration of the coating step. And we figured out that ZNO, sonicated, and IPA work the best. So in the image on the left, you can see there's 3 vials. So the first vial is ZNO shaken in water, and by shaken I mean we manually agitated with our hands, because this would actually be like the cheapest way to suspend it, but it didn't work very well as all of the nanowires are just sitting on the bottom. And then the other 2 vials are ZNO sonicated in water and ZNO sonicated in IPA. Although the water and IPA solutions look the same, they aren't, because after 15 minutes, the ZNO and water actually sunk, which is on the right image. So therefore, for the relevant duration of our coating step, which was 10 minutes, we chose to use ZNO and IPA. We performed physical characterization after we coated using SEM, and you can see that there's actually a significant amount of nanowires deposited on our cotton, which is good because it shows that it actually stuck to our cotton and didn't just fall off. But the nanowires are notably unaligned and they're actually clumped together. We were hoping to achieve a more even dispersion. So we performed electrical characterization with a multimeter, and we got these graphs. So you can see that the voltage we got was really weak, and furthermore, the results are very unreliable, and they were really hard to reproduce because we did this multiple times, and it was not consistent at all. So at the time, we predicted this was because of our poor coating, and we tried to improve our coating by submerging it multiple times, using different concentrations of nanowires, trying different ways of heating it to dry it. And we actually didn't realize at the time that the main reason this was poor was due to the unalignment of the nanowires. And we actually also thought that maybe it was the ZNO just not displaying a large enough piezoelectric response. So then we compared PVDF polymer to ZNO, because PVDF is like a commonly used piezoelectric polymer, which should give us a good reference. So that's why there's PVDF in the charts. And when you can see that the PVDF also had really poor response. So then we realized, okay, it's a deposition method that's at fault, and we were definitely not going to achieve the results we wanted if we continued with this kind of deposition method.
So in order to make a film that we feel like would meet our requirements, we decided that we would look to electrospinning as our method. So electrospinning we believe would work because you apply a high electric field which would allow you to align and evenly distribute your nanowires. We saw that it was proven to work in literature for similar applications, and we had consultation with the high voltage engineering lab, which led to confidence that this technique would work. So let's take a look at exactly how electrospinning works. So the liquid that you use is the material you want to deposit on your substrate, and it's mixed in with a solvent. So when you apply a high potential to the liquid through electrostatic repulsion, it causes it to jet out of your syringe tip, which you can see in the orange. As it travels through the air, charge migration to the surface causes it to eventually eject in a whipping-like fashion, which you can see in the blue. Finally, then it reaches your substrate and is deposited. This whipping fashion is not desirable due to the fact that your nanowires will have some characteristics of this and weaken the alignment that you get. So we had developed a fabrication method we wanted to use. So the plan was to dissolve our zinc oxide nanowires in a solution of DMF and acetic acid in a 5:1 volume-to-volume ratio, and then heat it on a hot plate for 6 hours at 60 degrees Celsius in order to fully dissolve it. And then we would use a high voltage power supply in order to apply a potential to the liquid, which would allow us to electrospin it onto our cotton substrate. So in order to avoid this whipping effect, we would move our substrate closer to the syringe, thereby avoiding the effect before it starts. So although this was the solution that we felt would be able to meet our goals, we were unable to pursue this method due to the fact that we did not have the necessary equipment. With that in mind, we chose to focus our attention on achieving our goals, doing what things we could through our available time.
So because we couldn't get access to the high voltage lab or any other electrospinner, we decided to focus on the other half of our project, which is essentially showing that we can actually harness the power from a film and translate that into something that could actually power a device. So to do this, we purchased a commercial PZT film and incorporated it into a sleeve. So essentially, we made a sleeve, and the film can be removed from it, which helps us meet our goals of durability, since you would never actually wash the film, so you would avoid mechanical agitation and the water damage that comes with washing. And we wanted to prove that we could actually power something, so we designed this comparator circuit coupled with a capacitor smoothing circuit. So this allowed us to actually change the film's variable output into something more constant, and we could actually power a blue LED. There's videos at the booth outside if you ever want to see it. So the principle of the circuit is shown in these two graphs. So the graph on the left has two signals. The blue is a sinusoidal curve, which was generated, the signal generated with an output of 1 hertz. And it's analogous to the variable output of the film, because as you can imagine, the film bends and flexes, so it's not constant. And then the comparator circuit changes this into pulses. And then when you add in capacitor smoothing, you get a more DC-like signal. So the capacitor smoothing circuit is essentially made up of two things: a rectifier, which allows positive voltage to pass through, and a capacitor, which stores the positive potential, so you can avoid any signal decay when the bending's not favorable, because you're not always going to get perfect bending every single time you tap or flex the film.
So let's look at the test setup that we used. So in order to normalize our displacement, we utilized the bend angle. So as you can see in this figure, we used a protractor to ensure the bend angle was consistent across tests. We chose to look at a bend angle from 0 to 60 degrees, as that matched the typical notion of the knee during walking. We also looked at the max bending, which would be analogous to having more intense physical activity and larger movements. So based on this, we did current and voltage measurements using a precision source measurement unit. So we decided to only include the film in the sleeve and not having our external circuit, which we deliberated on and decided for two reasons. The first reason is that we wanted to look at the effect of the film in the sleeve without any external circuits. And secondly, the purpose of this capacitor smoothing circuit with the comparator is not to enhance our signal, but instead transform it from a variable signal to a DC, and we had shown that that was possible already. So as you can see in these plots, when we had the max bending, we got a peak-to-peak voltage of 40 volts with a current of 2 microamps. And for 60-degree bending, we got a peak-to-peak voltage of 12 volts with 1 microamp current. So based on these results, we were reasonably sure we could meet our customer requirements. However, we needed to do further analysis to be sure. So we measured the median absolute voltage and current as a function of bend angle. So first, as you can see, there is a clear linear trend. Well, there's a fairly clear linear trend that you see. And when we used the 60-degree angle of bending, we found a power output of 0.52 microwatts. However, when we used our max bending, which is close to 180 degrees, a little bit under, we found a power output of 6.77 microwatts, which met our customer requirement. It's important to note that the max bending didn't display an exactly direct characteristic. Instead, it had a bit of exponential factor to it. And we believe that not only are we deforming the film more at this high angle, but a larger area of the film is deforming, which gives us that signal.
So now it's important to go back to our customer requirements to see what we actually achieved. Well, our primary goal of a minimum of 3 microwatts of power was clearly obtained, because as Josh mentioned, we actually got 6.7 microwatts at max bending. And we had a really, really light prototype, so the secondary goal of 10% less than clothing was also attained, just because when we weighed it, it was almost it was just 17 grams or 7 grams, so it's almost nothing. A goal that we think that could be achieved, but we didn't have time to test it, is the fabric lifetime of 1 year of 50 wash cycles, because you would never wash the film, so you would expect a standard piece of cotton fabric to be able to survive that. So we essentially didn't test that just due to time constraints, but we believe it could be met. And the goals we didn't meet were environmentally friendly disposal, 50 microwatts of power, and a profit margin of 50%, as the film is kind of expensive. So this leads to future work. Well, ideally, we'd want to perform electrospinning of the ZNO nanowires, following our original fabrication plan, onto the textile so we can obtain inline film, and it would utilize the intended technology of the zinc oxide nanowires, as the title of our project suggests. And we'd want to refine our existing circuit into a more lightweight and portable format that could be also incorporated into clothing to make our whole device a wearable textile. And lastly, we want to investigate protective coatings to protect our textile from the external environment. So this concludes our seminar presentation on our topic. Thank you. Do you have any questions?
Thank you. Okay, other than gesture at each other.
Just grill us. We know it's coming.
So, when you tried the PVDF, where did you put that? How did you use that?
You want to answer?
No, you can.
Okay. So we had it in a powder, and we basically dissolved it in or suspended it in a similar way that we suspended the zinc oxide nanowires.
The DMF and...
Yeah, we used our solution of IPA. The IPA solution, and then we wanted to match the two procedures to make sure that it was our method and not just the zinc oxide nanowires itself. So we tried to match both, test exactly.
So we essentially compared unpulled ZNO to unpulled PVDF.
Yeah.
Okay, so you've got your pair of socks, you dip them in your solution.
Essentially, yeah.
Then what do you connect where?
Well, okay, we apply the silver paste, and that acts as electrodes, and it also helps with the conductivity. And then you have the 2 electrodes, and you just put your probes onto it.
Okay, so it's a bit of a challenge to get them out
to
meet your PVDF. So cotton was a good substrate for grabbing hold of, but wasn't it really challenging in terms of how do you make continuous contact to something that's so complex?
See, that was the problem. You saw that it clumped, and you're talking about the ZNO on the cotton.
Yeah.
Yeah, you saw that it clumped in that. That's why we wanted to move to a method that used a higher electric field that would be able to more evenly distribute it. And that it would take more time as well to ensure that the film is more evenly dispersed. But again, you'd also need to look at the concentration to have something high enough to get a continuous, basically, conduction across it. So those were challenges that we were trying to address using the electrospinning.
Okay. And I wish I could understand my writing. Yeah, I'm not sure what that means, so I'll have to let you off the hook. Okay, thanks. So, I guess if I were to approach your problem, your problem specifications, there would be some red flags about zinc oxide as piezoelectric material with respect to your application. So I'm trying to figure out, I mean, even if you were able to align nanorods and have them in contact with each other, they seem to have some mechanical issues. I mean, if you're going to be constantly bending them back and forth, and that bending can be quite severe in fabric, can't they crack?
It is a possible problem. Again, we wanted to we were going to use our signal that we got based on our testing to see if it decayed over time of continuous use. So that would be one thing you would have to do durability tests for.
Didn't you already show? I mean, after three trials with the same. I guess you have a few samples, 3 trials with the same sample, and you go from
like crazy 40 to like negative.
A non-negligible signal
Yeah.
to a negligible signal. So I'm just trying. I mean, I can't resolve this in my head. It doesn't seem like zinc oxide is the right material because it has it doesn't. It's not very elastic. I mean, it's going to yield. It's going to fracture, and then your circuit's broken.
It is a bit more flexible in the nanowire form than if it's just regular zinc oxide. So that was one thing. And in literature, they had used it for some textile applications, not similar to this, but it was shown to bend, although they didn't do any durability studies. So that would be one issue. But the fact that it's safe for human use, like for skin contact, that's what made it so ideal for us.
And we were hoping to get far enough to use a protective coating and also do some tests, but we never got that far.
So you composite, basically.
Yeah.
Yeah.
Exactly.
Okay. Then one last quick question. If you go back to your initial tests where you were kind of
The first characterization?
dispersing and or dissolving the nanowires in some solution.
Oh yeah, I know this one.
Why did you pick these
Solvents
initially? Could you have done something?
Okay. Yeah, I can.
Water and IPA.
So
there are millions of different solvents.
yeah. Okay. So, yeah, I can answer that. So first of all, we chose water just because it's so easy, it's cheap and easily available. So that was the primary reason for that. And IPA was relatively accessible, and it's a fairly cheap solvent. So when we tested the two, the reason why we stuck with IPA is that the whole purpose of this is that it needs to be able to last the time that you do the coating step, stay dispersed. So since IPA was able to stay dispersed long enough, it met our application, easily accessible for us, and it was cheap.
Okay, but my core question is why? What is different between water and IPA? What's the property of the solvent that's important?
Well, we needed, for the nanowires, we needed a polar solvent we found in order to be able to dissolve these.
And then what's the quantity you can look up in a handbook that would tell you this?
I think. Oh, you mean what concentration we use?
No.
No, because that would be dependent on our
How do you know a solvent is polar?
I think it's we were reading literature and they suggested IPA, but we wanted to try water first anyways, just because it's cheaper. And then we just picked IPA because it worked in that piece of literature.
Is that your final answer?
I think so. I mean, I'm really, it was through a paper.
Thank you.
Questions for the audience?
One of your goals was environmental friendly. So what do you do with the clothes when it's the life is done?
Well, we
Landfill?
we never actually achieved that goal. But I guess what we had in mind is assuming we actually made a textile was some kind of recycling process at least, where because even if you throw out the clothes, it's bad, right? But at least if you could somehow at least clean the is, I don't know, like off the clothes or something, or off like that patch of textile, maybe we could then recycle that fabric in a different way and then like dispose of the nanowires like safely. So I guess like that was a thought we had.
One question before I let you go. I didn't understand how your 2 electrodes were placed on your textile. Can you explain that again?
Like how we put them?
How did you measure the voltage across your fabric once you had put the zinc oxide? Where were the 2 electrodes?
They were like across the fabric, so we would push down and bend it in a loop, and they were on the 2 sides.
Like if this is
So
a,
if this is the cloth, one is here, one is here,
yeah, essentially like one is here, one is here.
and then you bend it.
Yeah.
Okay. So do you think will that measure the voltage that is generated across your nanowire that is being compressed?
Well, we also had like silver tracks going across the whole thing, just to help with the conductivity, just like and to connect the 2 contacts.
Thanks.
Okay, thank you.